Hello, this is the first assignment of chapter 11. It's about fruit flies, and maybe you'll learn a little bit about biology here. Biologists are working with fruit flies, and they're mating them and looking at their genetic makeup. Each time there's dominant genes, capital R and capital N if you have taken biology. And the recessive genes are the lowercase letters, okay? The R is for the eye color, the N is for the wing type. And each offspring gets one gene for each of the two traits, one from each parent. So the biologists are predicting, or from experience, they think that the ratio will be like this. There will be 9 red-eyed straight-winged fruit flies. 3 will have red eyes and curly wings. 3 more will have white eyes and straight wings. And 1, must be the recessive gene, will be white eyes and curly. So the only way to get this outcome, I think, is to get both recessive genes. That's why it doesn't happen very often. To test their hypothesis about the distribution of the offspring, they there's your random, they randomly select fruit flies and mate them. Of the 200 offspring, here's the breakdown. 99 of them had red eyes and straight wings. 42 had red eyes and curly. 49 had white and straight, and 10 had white and curly. Okay. So what are we testing? What is our null and alternative? So we're essentially testing what their prediction is. So the null is that they're right, that the distribution of the eye color and the wing shape is the same as they predict. And they're predicting 9 to 3 to 3 to 1. That's from right here, 9 to 3 to 3 to 1. And the alternative is very easy. You can do some copying and pasting, because this first part is identical. Really, the only difference is we're not saying it's the same. We're saying it's different. It's different than what the biologists predict. We're not claiming what it's going to be. It's just that it's not going to be 9 to 3 to 3 to 1. So it's just going to be different. So then we're going to fill in this table to get our chi-squared test statistic. So what did they observe? You can pull these numbers from up here in the paragraph. 99 of them, that's right there. 42 were red with curly. 49 were white with straight wings. And 10 were white eyes and curly wings. Now, what would we expect to happen? Well, that is based on the null. And the null is based on this ratio, 9 to 3 to 3 to 1. So what we need to do is just add these up. What is 9 plus 3 plus 3 plus 1? Well, that is 16. Okay? So the expected counts come from the ratio. I should have left a little more space here. So for the first one, we had how many total? We had 200 total. Of 200, how many would you expect to be in this first group? Well, if you had 16 fruit flies, you would expect 9 of them to be red eyes and straight wings. So it's 9 out of 16. And we're taking that from a grand total of 200. So on the calculator, I would do 200 times 9/16. Like that. And so you get 112.5. Okay. Then furthermore, keep going. The next one is 3. We would expect 3 out of 16 to be the next group. So 200 times 3 out of 16 is 37.5. The next one down, the white with straight, that is again 3. So that's going to be the same as the one above it. And then the last group is only going to happen 1 out of every 16 fruit flies if their prediction is correct. Okay? So essentially what we're looking at is those expected counts. I'm also going to put them in my calculator because it can do some of this work for me, okay? So 99, 42, 49, 10, those are what we observed. What we expect is these numbers. Let me look at that. Okay, we're good. Because now as I'm looking at observed minus expected, yeah, I could do observed 99 minus 112.5. I could do that one at a time, and I could write them down, right? I could do it again, 42 minus 37.5. And that's fine and dandy, but I can also use my lists. I'm just going to go over to list 3, and I essentially just want to do this is L1, this is L2, this is L3, and I want my L3, I'm simply going to do equal to list 1 minus list 2. So I'm going to do that here. And then when I hit back down, there's my expected counts. And I didn't have to do it by hand, so to speak. Okay, so real quickly here, like what does this mean? This is telling me here that I was 13.5 lower than what I expected because it's negative. The next one, I was 4.5 fruit flies more than what I expected because this observed count was larger than the expected, and so on. Okay, now we simply square all of these numbers on the next column over. Again, you can do this by hand, but be careful. If you just square it like that, it's going to tell you it's negative. But we know better to put it in a parenthesis to safeguard against that, or just know that whenever you square anything, it's positive, okay? Or, I don't like doing this by hand. Go back to my lists. Go over to list 4, and I just want to square whatever is in list 3. And there you go. So there's a quick way to do that. So this was list 4, and I just made it, I just made it L3 squared. All right. Let's get down the rest of these. Okay. And now the last thing we do is I can do another list. This is going to be list 5. Okay. We want to essentially do observed minus expected. Well, isn't that right there? Observed minus expected squared, which that is list 4, L4. And I want to divide by expected. And which one is my expected? That is list 2. Make it bigger. So this is going to be L4. Clean that up a bit. Divided by L2. All right, this is L2. This is L4. And again, you could do this by hand, but I just don't really see the purpose to doing it by hand. So I'm going to go over to list 5, get rid of the data I had there, and I'm going to do L4 divided by L2. Boop. And there you have it. So those are my test statistics for each outcome. Okay, each outcome contributes to the chi-squared value, 3.526 we'll say, and 0.5. Okay, so that's how you do that on the calculator and save yourself some time. Essentially what we're learning here is like the one that's the smallest, well, these two are both pretty much the same. That's because they were very close to what you expected. They were only off by 2.5 and 4.5, which leads to a small chi-squared test statistic. The one that was the farthest away was this one, the first one. We were off by 13.5, and then you square that right here, so it gets even larger. which leads to a bigger test statistic. It is kind of tempered by dividing by the expected value because this expected value was bigger, okay? So in the end, actually, this one has the largest chi-squared value because it was almost the same difference, but when you're dividing by the expected value, this number is about a third of this number, so that makes a huge difference. What I'm trying to say is this cell here, the white with straight wings, these kind of fruit flies were the ones that differed the most from what we expected because it has the largest chi-squared value. The smallest one is 0.5, which means this type of fruit fly differed the least from what we expected. All right, calculate the chi-squared value. Well, that would just be adding up these numbers. And again, yuck, I don't want to do that by hand. So I have all those numbers right here. Let me get rid of list 6. I have them all right here in list 5. I just want to add up list 5. So I'm going to go stat calculate number 1 var stats, and I'm going to do list 5. Remember, it will give me the sum. It's the sigma, that capital E thingy, capital EX. So it is 6.186 repeating. Okay, that's my chi-squared value. Okay, there you have it. Now you can also do this. Number 4 says do this on the TI-84. There's a button that does this. Okay, I just put my calculator away. What was I thinking? So if you go to your test menu, where we've been for months and months now, it's down here on the bottom. It's letter D, chi-squared GOF test, chi-squared goodness of fit test. You click on that. Whoops. And I need to put my lists in. So it is list 1. Yep, list 1. What doesn't it like about that? It's giving me a domain error. Observed and expected. List 1 and list 2. That's what I want. Degrees of freedom would be 3. Let's try that. Oh, there we go. I just had the wrong degrees of freedom. So let me speak to that for a second. Degrees of freedom is always simply n minus 1. So in this case, what's n? N is that there are 4 different types of fruit flies in this situation. So the degrees of freedom is 3. So you set that. Then it worked. Then it gave me an actual, the chi-squared value. You can see it right there on the calculator. It matches what I had here. So that makes me feel good that I didn't screw anything up. And then my p-value, well, this is really, really close to 10%. So it's about 10%, 10.2%. Okay. So you are, again, what we are testing is how well does our data, here's our data, how well did that fit this ratio, this breakdown of 9 of these type, 3 of this type, 3 of this type, and 1 of the last type? Well, we found out that the p-value is about 10%. It never gave me an alpha, so I guess I should throw out in there that we'll do 0.05. But 0.10 is greater than 0.05, right? So what do we do over and over again? Our little chart here. Here's alpha. On the above alpha, we fail to reject the null. And down here, we reject the null, right? And 0.10 is up here, so we will fail to reject the null. So what does that mean? Well, essentially what that means is going back up here, we are not rejecting this. We more or less we do not have enough evidence for HA. So I would kind of go, we don't have that evidence. I wouldn't say we have significant evidence that this is true. We only say we have significant evidence if we are rejecting the null, but we're not rejecting the null, we're failing to reject it. So the way I would word this is that the data supports this. It doesn't prove it. It's not statistically significant that this is once and for all been proven to be true. Okay? So I would say there is evidence to support the biologist's claim and then restate their claim that the ratio of fruit flies is indeed 9 to 3 to 3 to 1. All right, here we go. Bye-bye.